Hey, Terry. So I'm David Perwitz from DeKunik, North America, and thank you very much to FenCan for having us. Thanks for allowing me to get up here and introduce Kyle Cartwright from Westeck Windows. As a player in the non-metallic reinforcement market, very excited to be participating. Kyle has been in the window industry for 23 years. Worked his way up from washing windows on the floor up to technical director at Westeck Windows for the last 12 years.
Pushed me out of my job.
Yeah, pushed Terry out of his job. Very excited that was able to work with both Kyle and Terry on development of a product that utilized non-metallic reinforcements to achieve some very impressive thermal numbers on a product. And so Kyle will talk about that a little bit. So without further ado, Kyle Cartwright.
Thank you, Dave. Okay, I'm going to jump right in. How can I get this up onto the... Perfect. I'm happy to have the option to sit. I typically pace, so I'll be back and forth through the stage. No guard load application here, I don't believe. So we'll jump right in. So quickly, going to generalize in some parts and then be specific in others. So we'll go over some material properties generally. We'll have a look at a horizontal slider from an NFRC and NAF's standpoint. I'll touch on some patio doors, and then I'll do a project-specific solution. So this is all based, my presentation is mainly based on non-metallic reinforcement, and I have some options because we do also produce windows with metallic reinforcement, and we'll go over that here as well. So generally speaking, we're getting our material properties from NFRC 101 here and the appendix noted in there. I believe this is pretty standard across the board for us here in Canada and North America. Just to touch on a couple of the values here. So we can see here in the red, we have a fiberglass, and this is a general property from Appendix A. So in terms of watts, 0.3 up against aluminum, 160, and then of course steel at 52. So that gives you a little bit of a gauge and for the different materials that are commonly used in reinforcement and their connectivity. Just a couple notes on the side of the jump and increase in thermal conductivity. Steel to aluminum, 200%. And certainly the one down at the bottom, fiberglass to aluminum, 53,000. It's a big one. I use those numbers specifically just to kind of show the jump. Okay. So these are our snaps from our NFRC certifications for our horizontal slider. And we have both steel and fiberglass options, again, for the comparison here. And this would just be for the gateway size. And just some visuals on the side here. The one at the top shows the steel reinforcement, so both in the interlock and the sash. And then the one on the bottom is the fiberglass option. So the fiberglass we produce for our products is not an off-the-shelf item. It's not a like-for-like in terms of geometry. So it's specifically designed and suited for that product. Now, this may not help my cause here, but I think it's important to state we have just a standard double glazed argon fill unit here. We have a steel reinforcement up at the top at 0.28, and then a quick conversion here. So 1.58, and then the fiberglass option at 1.53. So rightfully so, not a huge jump in performance. Sorry, I'm getting stuck here. And then in terms of NAFs, same window, two options, just a relatively small size, 71 by 56. Again, horizontal slider, same reinforcement methods as noted before. And then we can see the structural PG65 for the fiberglass versus a PG55 for the steel reinforcement. I think at some point we have to consider that steel is stiff and it doesn't want to deflect and it transfers loads to other areas. I think the failure point for the steel reinforced window was the screws at the top sheared off. So it's transferring load back into the attachment points and something's got to give. The fiberglass, on the other hand, was bending with the loads and allowing it to move. So takeaway from this slide, the steel is strong, it's stiff, doesn't always do what you think. So I have some deflection data from the exact same test results for both options. Fiberglass in the red, steel in the blue. Again, it's not a like for like comparison necessarily, but they are the same products, just different reinforcement. So here, I call this one test scenario 1. And essentially it is not jumping from PG rating 15 to 20 to 25. It's incrementally going up the pascals. I primarily do this for 2 reasons: to allow for a direct comparison and provide this deflection data to third-party engineers for their analysis as well. So you can see here that, in fact, deflection on the left, the steel was deflecting more as the test went on. And it starts to yield at points and doesn't necessarily return back to its place as the fiberglass would. So until I plotted these points and pulled the graph, this would be somewhat counterintuitive unless you went through this exercise. Test scenario 2 is us jumping from PG rating, PG 25, 30, 35, 40. And then, of course, the positive or design pressure versus a blowout. So you're going up and down, and cycling in that way. And again, the graph line is different. It shows different, but relatively speaking, the same outcome between the steel and the fiberglass. So I'm going to move into the patio door section here, but just to touch on the NFRC from the sliding window. Perhaps not the biggest performance upgrade between steel and fiberglass. Here's when we really start seeing a benefit. Same scenario, we have metallic reinforcement, and then we have a fiberglass reinforcement. On the images to the right, the one at the top is the steel, and the one on the bottom is a fiberglass. Again, not an off-the-shelf item, specifically designed to fit within that profile, specific geometry to provide structure and rigidity throughout the panel. And then again, a comparison between a double glazed, a triple glazed, and then aluminum reinforcement and the fiberglass reinforcement. So we can see here that this aluminum reinforcement in a triple glaze application, 1.59, just getting into a code minimum for sale. The fiberglass at the bottom, all things equal, just a difference in reinforcement, drops down to 1.36. The reason for the heightened performance here specifically is that for our patio door system, it's a fixed panel, reinforcement around all 4 sides. On a horizontal slider window, perhaps the reinforcement is interlock in the sash meeting rail, not necessarily around the perimeter of the frame. So on this application for a patio door, the fiberglass reinforcement has that much greater of an effect. In terms of, I don't have a slide here, but in terms of structural rigidity and the PG rating, we have of equal PG ratings for this product. We have a multi-slide system, so we go off panel sizes of 5x8 and a 4x9, roughly speaking, and we're up in the PGs, PG 25, PG 30. For the next step for heightened structural rating, at the bottom you can see the bottom right is the fiberglass. We insert steel inside the fiberglass. So it's a hybrid approach of using the fiberglass that retains the thermal performance and then adding the steel inside of the fiberglass for the stiffness, the strength, not necessarily to negatively affect the thermal performance. If that makes sense. Okay. So
Kyle, can I stop you for a second? Can you go back one? So talking about when you get into larger panels and you had to do some metallic reinforcing inside the fiberglass, do you have numbers, U-value numbers of what that impact was? Or was there any?
I don't at the moment have numbers for that additional reinforcement in there. That would be a real life scenario. NFRC standard size wouldn't have us put that steel in there because of the tested size, 2 meters by 2 meters.
Okay.
So no. Now, in a real life scenario where we're doing size specific modeling, that fiberglass just extends its performance, because now not only is the glass panel larger than the 2 meters by 2 meters standard size for NFRC, the glass to frame ratio is greater. So the numbers start dropping down. So the steel reinforcement, either we use it on the exterior panel or the interior panel, those would have a difference in real life values. But I would suspect they'd be marginal at best. Okay. So I'm going to run through this project-specific solution here because I think it's important and it kind of ties things together. So this is Whispering Horse Winery. It's based out of Chilliwack, BC. So it's local to where I work at Westeck in Chilliwack. And one of our customers came into the showroom one morning with this project. This is just a snapshot of the architectural drawings. So they're constructing a new tasting room in their facility, which is about 10 minutes away from our head office. This is a large window. There's 2 windows on this project. A little difficult to see. This is the north elevation. There's one on the south elevation as well. So our customer came into the showroom having not purchased anything from Westeck before. Perhaps just driving down the street. Our showroom is there. They came in. They were struggling with having a local manufacturer provide a local aluminum system for this application and code compliance. So I say local, I'm doing air quotes, because perhaps this other company has their facility in BC. Their local product is not a local product. The solutions that we have here is what I would like to call a North American product. Primarily, it's manufactured in Chilliwack, of course, but most of the materials, if not all materials, are based out of North America. And I think that is a solution that is still possible. We don't have to do everything overseas. I think in North America, for the most part, everything could be produced and manufactured here. So not only are we did help this person with a solution here that I'll go over, but also it's a local winery. The grapes are local. It's in their property. These windows were produced locally. They were produced by people employed locally. Everything about this solution is 100% what they were looking for. They didn't understand necessarily the benefits of the solution that we provided them, but when we talked through it with them and give them the logic behind some of the choices that we made here from a design stage, everything started to make sense, and they left feeling better about it. It wasn't a get it done situation necessarily, because there's 4 or 5 different ways we could have been code compliant with this exact same product. And I'm going to go through the solution that we chose. So new construction. Again, I spoke about the local suppliers and their ability to comply. 2 large window assemblies. So a couple customer-based design criteria. This is specifically what they wanted. A unitized system. Of course, this is a large system. We weren't able to produce and or ship as one piece, but I'll get into that. Seamless installation. The exterior, and it doesn't show very well here, will be cladded with insulation. The interior is all framed in with a welded steel member. They didn't want to, there's no drywall return. There's no way to hide the gaps between the windows to the rough opening, to the attachment points, etc. So it had to be seamless. And I'm not necessarily just talking about around the perimeter, but the joinery between the mullions. They didn't want to see any of that. Not necessarily an easy thing to do. but I'll show you some solutions here. And of course, the last one, make it work. Again, not necessarily considering the struggles. They asked us if we could do it. I said we could do it. I then went back to my office and started making some calls because I said we could do it. I was positive we could do it, and we ended up doing it. So again, this is a little old lady I use for reference just to gain the size of that window. That being said, she's probably coming in at 4'6", so it's a little bit of play there, but I think it really drives home the size of this window, and the photos and this doesn't do it justice until you're standing in front of it. Okay. So here's a photo of the building framing. Again, it's a welded steel structure and the wood being built around it. We did have to change the design of the original window based off the architectural drawings to allow for us to manufacture it in the way that we wanted to. Essentially, they had it's 4 panels wide. We went with 5 panels. So we're breaking up that window slightly, allowing for greater structure and to bring that down. So a unitized system for both factory and site build applications. So again, I mentioned that we are unable to, well, we probably could have, but it's unrealistic to make this as one unitized frame around the perimeter to ship. It'd be extremely heavy, unsafe for our workers, shipping, et cetera. And it just logistically doesn't make sense. So we opted to break it up into 2 pieces, still very large pieces. But the thought process there was to make it manageable, but keep it as few pieces as possible. One thing that I didn't want to do was to have this sent to site as 10 pieces and all mulled together on site and then tilted up like it was a barn or something. That being said, we did a pre-quote structural engineering analysis just to make sure, even though we said that we could do it, making sure that we are in the right area for costs, et cetera. And then design aspects of not only structural, thermal properties, but site assembly, shipping, ease of production, and then seamless execution. Could have designed this window 2, 3, 4 different ways. At the end, it all has to come together. My thought pattern was to utilize fiberglass reinforcement. I know I had to incorporate steel in some aspects, and we'll go over this here. And I'll explain why I chose to go that way. But I wanted it to come off the truck, go in to be installed. We had X amount of days on site to make that make that happen. Excuse me. And then also consideration for site glazing, cleaning the window, et cetera. So here are some design aspects that we had to incorporate. So on the left-hand side, it needs to be orientated the other way. This is the horizontal section. So essentially, this window here is our Revolution XL tilt and turn window series. These are all picture windows. Inside this frame and the mullion to the right is a fiberglass reinforcement. Traditionally, you could see a tube steel box in there. We opt to go with a fiberglass reinforcement where possible. And here are some of the design solutions. Horizontally, it's a mold product because we can't ship the perimeter frame. So we went full across with a 4x6 HSS post. Massively heavy. And that had to be incorporated within the installation sequence. The bottom section goes in, the top goes in, then the post, a couple different ways to go around that. But it took some time to figure out the best method to do that. On-site meetings with the third-party installer, with the customer, of course. He was always, well, he lives right next door, so he's always poking around when somebody is on site. And we had to make sure that everything goes together. The mullion section on the right-hand side there is the solution that we went for here. This is a mullion with a fiberglass reinforcement, and then all the steel structure is to the inside. It's warm. There's no bridging there. So it's not exposed to the elements. It's warm. It will always be the same temperature as the surrounding area inside the building, and thus not compromising the real life thermal performance of this window system. For a tilt and turn application in NFRC, there's no requirement necessarily to model this mullion. So we could label with a picture window, cram that interior mullion full of steel, and it would be arguably a viable solution. That would have the steel be inside of that mullion and then directly affecting the plane of insulation between the glass. Certainly not the best solution. This, unless is analyzed on a site-specific application, those true values would not really bring forward that value. Speaking to the customer about this solution, because it wasn't easy to do, they understood that the majority of the steel reinforcement is to the warm side. There's very little, if no transfer from exterior to interior, minus some fasteners. That's probably the best solution that we could come with. We need the steel. It has to be there for this size of the window. There's no getting around it. These are the windows as going in. So the bottom section you can see is now 5 panels. That went in first. The top section is 5 panels, the rake system there as well. And you can kind of see on the bottom the HSS post sitting there waiting to go in. So we had to bring the post into the building first. Then the windows are assembled on site, stacked. And this was the only visible attachment point. Not too many ways around this. So it's a bracket system. You can see the horizontal HSS post being attached back to the steel welded frame there. We cap our HSS post with a break shape aluminum. It's painted to match the windows. That's the seamless look they're looking for. These windows in particular are full finish paint. It's just a black paint. So the windows are black. The building structure around it is black. The post cover is black. The attachment pieces that are visible is black. You really would struggle to figure out 2 things. One, that this is primarily a vinyl window system, and 2, where this thing is being attached back to the building. Dave?
I'm just curious how you attach that post to the vinyl window, because it's a box shape, right? So how did you do that?
Painstakingly.
Just painstakingly?
So on the left-hand side here, I'm pointing at my screen, you can't see. This post is pre-drilled. So we have every 12 inches, there's pre-drilled holes. So we're attaching the post back to the vinyl system, horizontally through, I guess. So in the sequencing, the windows go in, the post goes in, the post is supported, attached back to the building structure, and then it's fastened back to the window horizontally throughout.
So Kyle, so just for clarity then, so the screws that attach to the window frame, you've obviously drilled holes at the top of that box as well to access.
Correct.
I assume.
Yes.
Yeah. Okay. Yeah. Okay. Makes
Again, that was a solution to help the ease of install. Doing that on site would be very problematic and time consuming. So we set up a press system, and we would just punch it all in-house. We couldn't just put it up on a drill press because this, I don't know how much this weighs, but it's very heavy. And this window is, I don't know, 30 foot. So we had a manual punch system. This was pre-drilled and countersunk on the floor outside.
Can you go to the photo that shows the open frame? So that section on the bottom is 30 feet across, is that right?
The width, yeah,
Okay. And that's all one perimeter frame with vertical mullions.
correct.
Where'd you get 30-foot long extrusion?
We don't get 30-foot long
Yeah.
extrusions.
The Kunik, I know they're terrible to work with.
No. Sorry, Dave.
Oh, is Dave here?
Yeah, he's in the back. They provide us with the longest material that we could get our hands on. What we do, and this is one of the benefits of a vinyl system, we butt weld. So we do, it's a mitered corner welded around the sides, and then it butts weld, yeah. Thanks, Terry. It's all sanded and painted, yeah. You wouldn't be able to tell. No. No. Yeah. So good question, Dave, about the attachment points, because that's the thing. You can't just put a post up there and not attach it back to the window. It is a messy liability. So this one may be a little tough to see. I'll come over here. So again, we have, thank you. This is the horizontal. The cap is on before the verticals go in because there's no attachment points to be visible. So the attachment points for this vertical back to the horizontal is the bracket system on the right-hand side. So to have it as seamless as possible, the bracket system goes in, the vertical is notched out, the vertical goes in, attached back to the bracket, attached back to the mullion, capped. All of these vinyl materials we had in-house already from our supplier, and we just don't, it's not meant to do this necessarily, but this is a product that we have with these mullions and this window wall system NAFS tested, and we're utilizing parts and pieces that we do have that will work in an application like this. That is the final product. So you can see the look that they were going for. I think that we captured it fairly well. 2 windows on the job. They were not inexpensive. This is simply just a double glaze system. It could accept a triple glaze. But one thing I wanted to touch on too is that the comment of needing to go to triple glaze, we hear it all the time, and the costs associated. A solution that we came up with, we didn't come up with it, one that we utilize at Westeck is the fiberglass reinforcement. Because if your end goal is to receive an NFRC value of X or Y, there's 3 or 4 different ways to go there. You could do steel reinforcement in a triple glaze. You could do fiberglass reinforcement in a double glaze. If the end result is a U factor that you're looking for, and you get there in 2 different ways, which way makes more sense for that manufacturer or for the customer? Most of our systems can do a double or triple glaze anyways, but if you are, and we saw this too as well, supply chain issues, glass allotments, it becomes a problem. You can get steel off the shelf if you have fiberglass that you're bringing it in. If you can only get X amount of triple glaze IGUs for a certain amount of time, if you're on a quota of some sort, it's a problem. So to have a fiberglass reinforcement that helps bring the U factors down in those applications, both NFRC standard size values and real life scenarios, if you can deal with the structural application, such as this window, then it's almost a win-win. And I promised Terry that I would not go over my allotments. I hammered through it pretty quickly, but I did want to leave some space for questions or comments or conversation about a fiberglass reinforcement based solution for window systems.
So I'll start while everybody else gets their thoughts together. Kyle, thank you very much for presenting. I know how, I think as window door manufacturers presenting to window and door manufacturers, it's a bit vulnerable. So I think it takes a lot of courage to come up and show a solution that frankly is innovative. I think you guys did a great job. So I'll get to my question, which is your horizontal beam, how much energy did you put into having, because you're going to have that mechanical connection point there at the horizontal.
Yes.
And I always had issues with essentially the water there. So is that just a glazing, that's just a caulking bead on the outside, or how did you guys deal with your horizontal plane when it came to drainage?
Back up. I think I could explain this a little bit better. I'm just going to, sorry, give me 1 second here. It didn't seem like I had so many slides when I was talking through them. So this is a horizontal section again. We have a cap piece here that is pretty standard for anything that we mull. So if we orientate it this way, this is where the seal would be right here. So essentially, if all things equal, this is never going to see any weather.
Totally agreed.
Yeah.
But your outside connection between those two frames are going to have that seam. So what you're saying is on the exterior, you've got a capping solution that is essentially creating that barrier. So
That's correct. Yeah, and it is well sealed in there. And in fact, a true story. We were at the lab. My team and I were at the lab in Coquitlam with some other NAFs testing, and we had to go to this site because there's one thing that they left uncompleted on site. It was the cap. So we did have to rush down there to fire that in and make sure it was sealed off properly, because it is a large window and it's exposed.
And the worst thing you've got is that maintenance in 3 years to come back and re-caulk it if you decide the caulking solution. So the capping makes sense.
Right. Yeah. Yeah.
So, Kyle, I'd imagine when you're dealing with like a client, a homeowner, someone who's kind of like the end user as well, it's pretty easy to have these conversations on, hitting the metrics as well as maybe being a little smarter about it. How about when you're bidding on projects where design professionals have already kind of made some decisions and they're saying, no, we want triple glazed, they're used to steel, are you getting traction when you're proposing some of these smarter or alternative options, or does it kind of fall on deaf ears?
I wouldn't say it falls on deaf ears. It depends on how early you get at those ears.
Yeah.
So we have quite a few sales reps, and if they just want a window and they just need to meet the value, then whatever our quoting system kicks out is what it kicks out.
Mm-hmm.
Luckily for Westeck, we are able to get out in front of this job and do exactly what we thought we should do here.
Mm.
So like I mentioned, we have a lot of fiberglass options for reinforcement, and they provide values, and it's and pros and cons. It's not all realistically pros and cons.
Sure.
But there are design solutions, and if they feel that the consultants already are going with steel and they don't want to change it, if they need to meet a specific design pressure for the windows structurally, if a solution for us, and you could debate this being an intrusive solution to have steel reinforcement to the interior, that might be something that is the kicking point for typical window applications. You see a casement window, it's got a mullion, there's nothing to the inside necessarily. So that additional reinforcement is going to the inside. So if you don't have a design solution, like I showed in the photos there, to make it pretty, then they don't want the extra work. They don't want to deal with the air barrier and the ceiling, because we're essentially adding work to somebody else's scope if Westeck isn't or the installer isn't already part of that.
Yeah.
So for the most part, single family homes on these large windows, we have to come up with some sort of solution. The smaller windows, if you're building a 3.0, 6.0, do we need a solution like this? Perhaps not.
Yeah.
But if we're meeting the values. So I do struggle at times getting this point across. I don't know. More of these will added to the catalog of data and proven results. I think maybe that's key. We've done this now. Let's look at the serviceability of the product and see if the solution provides that level of comfort for somebody, because I understand maybe going out on a limb on this weird thought and that is a risk. But the more of these we do and the more logic we can bring to that, the risk goes down.
Yeah, I totally agree. It's always an interesting thing when window guys are brought in after all the decisions have been made. So
Yeah, thank you.
I think that this is, it's pretty innovative, because myself coming out of the PVC window industry, we all struggled with figuring out how are we going to get enough reinforcing into this mullion to meet the requirements. Well, hang on a second. Why does it have to stay inside the mullion? And in fact, if we put it on the inside of the window, we gain some benefits by it not becoming a thermal bridge. And once the client accepts this internal intrusion, I mean, you're good to go. And in fact, if you go and look at any of the aluminum metal systems that are large, they all protrude inward of the building. So it's not, you know, once they accept that, yeah, you could do this in vinyl systems, but it's metal, but it looks like the window, I think it's a win-win all around, right? So
I would agree with you there. And I think maybe the thought process of aluminum or steel, it's stronger, it's stiffer. It doesn't have to be that way.
yeah.
Back to the
Scott?
prior presentation, you probably didn't have to do an LCA for this because it's in Chilliwack and not Vancouver. But you do end up with a story to tell there, probably too, on the embodied carbon side. I would think even with the steel reinforcement using the fiberglass I think it's slightly better than it's more than slightly better than aluminum. I think it's probably better from that perspective.
Yeah, you're correct. We didn't have to jump through all those hoops. Not simply because it was in Chilliwack. It wasn't a requirement for the job. And in fact, we could have done far worse. We could have had a similar window that met all of the values we need structurally, thermally, all within a code compliance scenario, going about it in a different method. So we achieved the end goal, but by doing something new, not only for this customer, certainly, but almost to prove a point that these sorts of applications are possible. And there's, of course, pros and cons, but majority pros going this way.
Just so we're all clear,
sorry.
he was joking about the LCA in Vancouver. That's not a thing.
Yeah.
Yet.
So you're talking
Yeah,
about
you're-
embodied carbon
Not for wind.
calculations. So you're talking about the original design was 4 lights across and you went to 5.
Yes, sir.
Was that an engineering restriction or what caused that change?
That's correct. Yeah.
Was
Just to
engineering?
break it up a little bit more. So the steel that you saw, that was internal steel, that whole section was filled on some of those mullions. If we kept it with the 4 panels, we would have to exceed that somehow.
Okay.
So it would still be possible, but we'd have to look at other solutions for capping that internally somehow. But we already had the pieces, the parts and pieces, the vinyl, the steel tubes, the steel blades are easily available. It's just the way we went. And also, it wasn't that bad of a situation for them to concede on. 4 panels versus 5. The design was changing anyways, but I think it was a reasonable solution to get the most out of that.
Cool.
So I was surprised to see that your main structural member spanned the longest span, because with deflection of structural members, it increases with the cube of the length and it decreases with the cube of the depth. And cube over
How
cube.
tall was this system?
Not off the top of my head.
Because you're saying 30 feet across.
25 at the peak.
So 25 to the peak.
Yeah.
Yeah.
So it's surprising that you were able to make the main structural member 30 feet long. But I guess you must have done the engineering calculations on it. And so what methods did you use to do that engineering calculation?
So we engage we have a couple third-party engineers that we use at Westeck, and we brought it to them. It was a design criteria also for the customer. They wanted a horizontal running through. So if we went vertically, I agree with you, there's benefits structurally to going vertically. Then we would likely have to send that in 1, 2, 3, 4 different pieces instead of 2. So a slight drawback there.
Yeah.
So again, many different solutions. With those large posts, we saw one of the anchoring brackets visible.
Mhm.
We would have to have more of those visible. So one of the criteria for a seamless install and to not have visible attachment points, we would, instead of 2, we would have 10.
So my second question is, so that horizontal member that's 6 inches deep by 4 inches tall, was it also designed to bear the weight loads of the units above, and not deflect too much in the vertical direction? Or did it transfer the loads down through the windows to the floor?
So we had 2 options for the post. We could have went with more of a square instead of the rectangle, but we chose the rectangle. It was difficult to cap. Just because of the break shape aluminum is difficult to get. But that post is also supported by the verticals that we saw there. slightly supported by the verticals that are underneath it, slightly transferred back to the window. But the IGUs in the window above are even just the way that that window system works is transferred to below, not necessarily back into that beam. So it's 4x6 to deal with the wind loads in that, not necessarily to hold the weight of the windows above.
And so what was your calculated deflection at the design pressure for that? Was it around L over 175 or was it much less than L over 175?
I have two answers for that. It's whatever our structural engineer said it needed to be.
Yeah.
And my assumption that it would be the
L over 175, probably. Yeah, I would think.
and of course, as you know, we have NAFS testing. It can deflect to whatever we want. If we're going class LC, that's not happening in this scenario. Then we have to do the L over 175. We have the verticals with the steel, plus the fiberglass, plus the extra blades, up into a point where that all the extra blades of steel wouldn't be sufficient. Then we have a new design solution. So the verticals on the bottom were full packs of steel, essentially. So that was pretty maxed out for that reinforcement. Had they come back and said, well, this doesn't quite work, which they did once, that's why we're 4x6 and not a 4x4. But, you know, it is all good from their side of things.
So you said it was about 25 feet tall in 2 sections. So that means each section was about 12 feet tall. How did you get it there?
Again, painstakingly.
Carry it down the road because it was pretty close to you guys, right?
I think the bottom section itself is 9 feet, roughly.
Okay.
So 25 at the peak, but it's not an equal split.
Okay.
But one of the design solutions, or how we came about all of this, was the safe offload of the truck. This was a flat surface, so we loaded on our dock. There's no lifting in that, and it was we pulled right up to the truck, just down the ramp. The offload went quite well. So had they been 12 feet, we would have shipping constraints to deal with that.
Or something.
Yeah.
Okay.
But those heights of both of those fell within our shipping constraints.
Okay.
So we were able to do that. If we were not able to do that, maybe we would have to go vertical sections, because one section would be then, I don't know, 8 foot by 20.
Yeah.
So you ship it horizontally that way.
A great presentation, Kyle. It's nice to see manufacturers think out of the box. Dave, you stole my deflection question. So I got to go to my backup. What type of glazing method did you use? Wet, dry?
That system is a dry glaze. So it's just a double gasketed system, which is nice. And it's an interior glazed as well, which is also nice for that application there. So that's a product design there. It wasn't a choice of us doing a wet or dry seal there.
Hi, my name's Kelvin from Layton Consulting. I have a question. How did you do, what was your fastening strategy for the head sill and jam? And did you allow for vertical deflection?
So we went through the frame on the sills. It's installation angle to the bottom. And then around the jams and the header, we just had to go straight through the frame into the building structure. So at the top and the peak, they're more of like a floating screw. They're in there to hold it up. It's fairly rigid already. That's how we had to do it. And we were able to do that because it's a site glaze system. So we had access through there. And also part of the solutions for ease of install, it was all pre-drilled in our facility. So we designed the fastening method, spacing, top and bottom, and that fastening pattern. Pre-drilled it. They went to site, fired in.
So yeah. So did you have any concerns with, it's a 5-wide system. Did you have any concerns with tolerance stacking?
Yes. So, and that's a great question. Tolerance in terms of material fabrication.
Well, yeah, because let's say you were over by 1 millimeter in all your units. Now you've gained 5 millimeters, right? And you're fitting it tight to the assembly. It's not a regular, installation with like a 1/2-inch rough opening gap on all of the sides, right? So, I would have expected once you got using our manufacturing tolerances, I'm sorry, that they tell me that's the best that they can achieve on vinyl window frames, I'd be really worried about it being like plus 5 or 6 or minus 5 or 6 millimeters.
But was the product tight to the rough open? No, you wouldn't do that.
We did allow some space. So I think we had about 3/8 of space between the steel structure and the window itself. And I agree with you with the tolerance. That's another reason we went with the 2 systems. So we only had 2 welded frames instead of the 5 welded frames.
Yeah.
So of course you have to allow for that tolerance. It needs to be considered, or you're right. You do the one on the left, 1, 2, 3, doesn't fit. And also those 2 windows are the same, but they're not. They're off by 3/8 from one side to the other. So multiple site visits throughout the process, which is easy because it was close to our head office. So those windows aren't the same size, even though they appear to be. But great consideration, though. You have to do that. You have to think ahead, and that's one of the reasons why we went with the double.
What
That
low
has
E
caught
did you
me
use?
before, and that is painful to deal with, and you wouldn't be able to deal with it. You'd have to remake one of the sections to account for that tolerance being out by X amount. Not something we wanted to do.
Did you use a low solar gain on that south elevation or on both elevations?
We didn't use a high solar gain.
No.
That's-
You could heat the
That's a
place
question.
year round, no problem.
well, that
You're-
again, that is one of the problems, and I think within that system and with the fiberglass reinforcement around the perimeter, we didn't have to play with the glass too much.
Yeah.
So
But from a solar gain perspective, did they ask for a low solar gain glazing or they didn't?
typical glazing,
Okay.
but without running that the ER path, and we're not trying to hide a high U factor with a high solar heat gain. So it went not, it didn't go unnoticed, but we certainly wouldn't have put a high solar gain product in there to achieve whatever value they're looking for. That would have been not good.
Yeah. Okay. All right. Thanks, Kyle. Appreciate it. Good job.
That's it. Okay. Thank you.